Now, in order to carry on with our study of analysis, we will start now with a series of lectures about set theory. More particularly, we will talk about the elementary aspects of axiomatic set theory, and that's important. Axiomatic set theory. Now, as usual, I will be following Tao's book on Analysis 1 because, well, first of all, because it is a very good book, and I very much like the way he makes a parallelism between the natural numbers, as we have been seeing until now, and the set theory. You will see that we want to introduce, we want to follow very closely the same scheme that we have used in order to define the natural numbers. Remember that we started with Peano's axioms, and in following the same line of thought, we want to introduce set theory by agreeing between you and me what would be a good way of doing that. But first of all, I would like to remind you of what an axiom is. I have done so in the past, I believe, but this is something very important, at least it's very important to me, because this is something which used to confuse me a lot when I was a student, because it felt as if axioms were just fallen from the sky, and it is not like that. It's not that somebody one day decided to sit in a chair and to write down a list of brilliant axioms which would allow you to define or to work out a full theory of something. It's not like that. Let's start. Probably the best way to start would be to I'm going to go back to the root of the word axiom. So this is coming, as usual, from an ancient Greek word. I still believe that ancient Greeks were aliens because they did not resemble any other human being that I have known. That was, of course, a joke. But in any case, in Greek, in ancient Greek, we have the word axioma, which is written like this. This is an alpha. Axioma. And axioma means that which seems to be fair, just, what is evident, something which does not require a proof. And this word is stemming from the verb axiom, which is this one here. Axiom. So, this is considered to be a long vowel, so that you go back to the second one from the end, which is why the pitch is here, axiom, which means to value something. And that word, axiom, is stemming from the word axios. axios. And axios means valuable, something which deserves your attention, something that is worth of your yes, something which is precious, right? So to ancient Greek philosophers, an axiom was something which seemed to be true without requiring of any kind of proof, right? So when we define a set of axioms to work out a theory, we are agreeing that we have a list of statements upon which you and I we agree because they seem just, fair, evident. We don't have to prove them, and unless we agree, we cannot work out that theory. So I will present you that list of axioms, of sentences, and as a kind of a proposition. Do you agree with me that this makes sense and that we don't have to define this? We don't require a proof for what I'm going to explain you here. These 3 sentences, 4 sentences, statements, whatever, do not require proof. Do you agree with me that this makes sense, and that I have to wait for you to say yes, it makes sense, because otherwise I will not be able to carry on talking. So this is the essence of an axiom. So in this series of lectures, we are going to introduce set theory because it's an important thing to take into account. We're not going to follow a rigorous description of Euclidean geometry, for instance, but we need to introduce that geometry using the real number system via the Cartesian coordinate system. And therefore, it is important that set theory is introduced. It is not going to be the main focus of the lectures, of course, but we're going to at least see the most elementary aspects of axiomatic set theory, again following Tao's book. So if you feel like reading, you could just simply skip all of these lectures and just read the book. That's what I actually recommend. But anyway, this is meant as a summary to a group of students who are attending one of my courses. So we are going to start with the fundamentals of the theory. And again, the same way we introduced the natural numbers, and we have now a rather clear concept of what the natural numbers are, and why 6 is not the same thing as 5. I'm going to introduce a series of axioms, which is going to be actually a list of probably too many axioms. Why is that? Well, that's because although ideally the best thing would be to keep the list of axioms as small or short as possible, for pedagogical reasons, it is interesting to abuse a little bit the concept of axiom, at least within the context of a mathematical theory, and add a couple more of axioms than needed, because they will help you to understand the more general ones. So that I will introduce axioms for, say, very specific cases, to then introduce the axiom for the more of a more general case. We could have started with a more general case because that can always be reduced to the lower range, if you want, case. But again, for pedagogical reasons, I think it is very useful to do actually the contrary. And again, this is the way that Tao follows and uses in his book. Okay, so let's start with axiom number 1. I'm going to ask you to agree with me on this. So this is a pact between you and me. Well, actually, this is not quite an axiom. This is going to be, excuse me, this is, no. Let me back up. This is not going to be an axiom. I'm going to start with a definition. Okay. I'm going to define something like this. So, I'm going to say that a set A is any unordered collection of objects. And please remark that I am not defining objects right now. And I'm not doing that on purpose because it could lead to an infinite circular trap. So just relax and enjoy. Okay? So a set A is going to be any unordered collection of objects. For instance, say, I don't know, 6, 3, 2, 321. Now, if X is an object, then we say that X lies in A, or also X is an element of A, and that we write it like this, if that X is in the collection. For instance, in this set here, 321 lies in that collection. So we say that 321 is an element of that set. Now, this definition is quite intuitive, but there are a lot of open questions which it does not address. For instance, what kind of collections of objects are considered to be sets, and how do you define operations? It is a quite boring thing. We have defined an object, something, the notion of set, but we cannot do anything with it. Okay, but first of all, we're going to consider sets to be a type of object. And that leads us to the first axiom. Now, yes, now I am correct. To the first axiom. Sets are objects. This is going to be our first axiom. And I want you to agree with me. So, if A is a set, then, because of this axiom, A must be an object. In particular, also, if you have two sets, say Y and Z, you can ask the question whether Y is contained in Z as an object, like these two in the previous set, or whether Z is contained in Y, because they are objects. That means that you can define sets with sets. So, for instance, in the previous example, 6, 3, 2, we could have used a set here, for instance, 2 and 3, as an object of the set, and everything is fine. As a remark, there is a special case of set theory, which is called the pure set theory, in which all objects that you consider are sets, so that you don't work with anything which is not a set. In that case, for instance, the empty set, which we will define, the empty set, is identified with these two curly brackets. Number 1, for instance, could be identified with the singleton. I have not yet defined what a singleton is, but it's a set with just one object, and with the singleton of the empty set. Number 2, for instance, could be identified with the set containing the elements, the objects 0 and 1, but because we want to work with sets, we could replace this with, well, first with this one, and then this one over here, so that you would have a mass 1, 2, 3, 4, and 5. Right? No, this one too much. And so forth. In principle, pure set theory, at least conceptually, seems to be an easier way of working with sets and set theory, but in practice it is not. In any case, it turns out to be, because we're human beings and we live in a world, in a physical world, it turns out that for us it is easier, at least conceptually, to work with impure set theories. Now, the two types of theory are more or less equivalent for the goal of doing mathematics, but we're not going to go into pure set theory. This was just a simple remark. Now what we have is that if X is an object and A is a set, it makes sense to ask whether X lies in that set or not. So you have only two possibilities: X lies in A, or X does not lie in A. If A was not a set, it would not make sense to ask whether X lies in A, the same way that it does not make sense to ask whether 7 lies in 1. Okay, now we move on. We have defined what is a set. Remember that it is defined to be an ordered collection of objects. We have seen that we have agreed, you and I, with an axiom that sets are objects, and we have mentioned the fact that if you have an object, that object might lie in A or might not. But when do you consider two sets to be equal? Well, you can think of this set 3, 9, 13, and 15, and 15, 3, 13, and 9 to be exactly the same set. Why is that? That's because we have defined sets to be an ordered collection of objects. So we don't care about the order in which you are placing the elements in the set. Now, on the other hand, these two sets are different from 15, 3, and 13. So these sets are not equal because you are lacking one object. So we're going to formalize this by introducing another axiom. And again, I'm going to ask you in a rhetorical way, of course, rhetorical way, to agree with me. And I say rhetorical because I'm going to assume that you agree with me, otherwise we could not move on. I've been reading too much of Aristotle recently, which is why I say rhetoric before. But anyway, so axiom number 2, equality of sets. We say that two sets, A and B, are equal, so that A equals B, if and only if, which means that we have two arrows, one going this direction and the one going that direction, and that is equivalent to just drawing this kind of arrow, this. If and only if for any element of A that you might consider, that element is going to be contained in B and the other way around. So that for every X lying in A, then X must lie in B, and the same way interchanging A and B. In principle, although this notation, I'm using this notation for every if and only if like this, because I want to save. I don't want to, constantly keep erasing the blackboard. But in principle, try not to abuse. At least this is my personal advice. Try not to abuse of these symbols because it's going to look messy. Try to write it explicitly. Okay. So this axiom means that the sets 1, 2, 3, 4, and 5, and 3, 4, 5, 2, and 1 are the same sets because they contain exactly the same elements. And by the way, they are also identical, they are equal to the set 3, 3, 3, 4, 4, 5, 2, and 1. Why is that? Because the repetition is irrelevant. We don't care. It does not change the status of the elements in the set. At this point, I must remark that so when we say is an element of, so this symbol here, this obeys the axiom of substitution. And this axiom I have explained in a different video about mathematical logic. Because of this, any operation that we will define will obey the axiom of substitution, with the proviso that you can define that operation in terms of that lies in symbol. But at the same time, if you notice, of course, we don't know, we don't understand, we have not introduced, and I will not introduce, the notion of first and last element because because these would not respect the axiom of substitution. Now, we have introduced the definition of set. We have introduced two axioms. First of all, sets are objects, and we have also introduced the axiom about the equality of sets. Now we turn to the important question of identifying what objects are sets and what objects cannot be considered as sets. And again, remember the natural numbers. We are following the same line of thought. The same way we introduced a number, and that natural number, which we declare to be a natural number, 0. We want to introduce now, we want to agree, you and me, on the existence of a set, which we're going to call the empty set, and that set is not going to contain any elements. And as you can see, that empty set, so this is the action 3, first of all, action 3. The empty set, which we write like this, plays the role of what used to be, what is 0 in the natural numbers. And remember that we also we agreed, you and I, that 0 is a natural number. So you and I are going to agree that there is a set, which is the empty set, and it does not contain any element. That means that for every object x that you can think of, x does not lie in the empty set. The empty set sometimes is also written like this, and it is important to remark that there is only one empty set. If you had two different empty sets, say this one and this one, it turns out that the two of them must be equal because of the previous axiom. And I'm going to ask you to prove that. So why is that? Okay, so thanks to this axiom, we can introduce now a lemma, which is the single choice lemma. And that lemma goes like this. So single choice. Now, imagine that A is not the empty set. So we have a non-empty set. Then there exists an object x such that that x lies in A. How do you prove that? I'm going to leave that for you as well. But the point here is that you have to just follow. So you have to prove it by contradiction. If you assume that there does not exist any object, then you will run into a contradiction, and therefore the contrary is correct. Now, note that the empty set is not necessarily the same thing as 0. One thing is a set, the other thing is a number. But in any case, later in these lectures, we'll talk about the cardinality of the empty set, and we will see that that cardinality is 0. Now, we have defined the equivalent. We have introduced or presented an axiom that would be much more accurate. We have presented an axiom which is the equivalent to the natural number 0 in the natural numbers. Now, there is not much that you can do with 0, and the same way, there is not much that you can do with just one set, which is the empty set. The whole set theory would be extremely boring if you only had the empty set. So the same way we moved forward in the previous lectures, and we talked about successions, etc. We're going to increment. We're going to increase our variety of possible sets. And how do you do that? Well, you do that with axioms. So I'm going to again ask you to agree with me on this. Action number 4. Do you think it is a good idea to talk about a set which only contains one object? Does it make sense that such a thing exists? I think so, and I'm going to assume that you agree with me, because you cannot talk to me right now. So if you have any object, say A, then there is one set whose only element is A, and it's this one. And I'm going to call that thing the Singleton set. Now, if you have a different object, let me rephrase that. For any object that you can think of, if X belongs to that singleton, then by force X is A. X equals to A. If and only if. So X is allowed to lie in that singleton if and only if X is exactly that element A. Moreover, if you have two objects, say A and B, there is one set whose only elements are those, and it is this one, A and B. And I'm going to call this the pair set formed by the elements A and B. And the same way as before, for any object that you can think of, that object lies in this pair set if and only if X, or whatever you have called it, is equals to A or equals to B. Now, think of this. So for any object X lies in A, in the pair set of A and B, if and only if X is A or X is B. Now, remember that implicitly we are saying here with that or, because it's inclusive, that there is also the possibility that X equals A and X equals B. So it could be that X equals A equals B. And in that case, what would happen? Well, we would have a set containing A and A. But because we don't care about repetition, this pair set turns out to be the singleton set of A, right? Now, we have derived the existence of the singleton set A from the pair set A and B. And this is a wonderful example of what I was saying at the beginning of the talk. It's not a talk, it's a lecture. But anyway, when I was saying that I'm going to introduce a larger number of axioms than required for you to understand better the more general axioms. So I could have started with a singleton set, with a pair set, and move or mention that you can reduce it and mention just the existence of the singleton set, because it's just a particular example of the pair set. Now, by the way, I have said here that this is equals to A, but I also want you to prove it. Another thing that you must notice is that axiom number 2 ensures that the pair set AB is identical to the pair set B and A. And again, I want you to prove it. Why? Why is that? Okay, now in principle we could move on, right, and say, okay, we have defined a pair set. What about I don't know, pentaplets or quadruplets or triplets? But that would be extremely tedious, right? So if you think about it, it turns out that the pair set formed by A and B can be generalized. But how do you do that? I don't want to go through, triplets, quadruplets, etc. because, I'm going to run out of time. I will die before that. So how do you introduce something which allows you to define sets with a larger and larger and larger number of objects? Well, that is going to be possible thanks to the introduction of, guess, another axiom. But before we move on, I would like to mention that because the empty set is a set and therefore an object, we also have something which is a singleton set of the empty set, right? It's a set whose only element is the empty set, but this, in turn, is also a set. Also, the singleton set of the singleton set is a set itself, and the pair set of the empty set and the singleton set of the empty set is also set. And the interesting thing is that all of these sets are different from each other. Also like this, and I don't know how to draw it, but well, this is circular, right? So this one is different from this one, and that one, and the same for all of them. And I'm going to ask you why. Why is that? So you go ahead and prove this. Okay, but anyway, let's go back to the task of creating larger and larger sets. And as I said before, we can do that thanks to another axiom. Now that axiom is going to be the pairwise union. So this is going to be axiom number 5, the pairwise union. Pairwise union. So consider two sets, A and B. So we're going to call the union of A and B this thing here, and it will consist of all elements which belong to A or B, or both, so that an element X belongs to the union of A and B if and only if X lies in A or X lies in B, or implicitly, I'm not saying that, X belongs to A and B, because that or is by default inclusive. And this is something I talked about in the lectures about mathematical logic. It is important to note that if you have 3 sets, like A, B, and A tilde, and you have that A equals A tilde, then A union B is equal to A tilde union B. And in order to prove that, and I'm going to ask you to do it, you will need axiom 5, and 2. And the same way, of course, applies to B and hypothetical B tilde. Therefore, the operation of union, which we have just introduced with its axiom, and you and I, we have agreed on that, obeys the axiom of substitution, and therefore it is well defined on sets. Now we can define some properties about the union with a lemma. So if A and B are objects, then the pair set A and B is equal to the union of the singleton of A and the singleton of B. Now, if A, B, and C are sets, then the union operation is commutative. So we have these three sets, A, B, and C. And we have that A union B is the same thing as B union A, but also associative, so that you have the union of A and B, and we make a union of that with C. That thing turns out to be the same as A union the union of B and C. And finally, we have that the union of a set with itself is the same thing as the union of that set with the empty set, because of commutation, the commutative property. That's the same thing as the union of the empty set and A, and that's A. Now, I would like you to prove that what I said, each one of these things. But the way you do it is by looking at the left-hand side of this and the right-hand side. So this thing here is a set, all of it, right? And this thing here is a set as well, all of it. So all you have to prove is that for any element lying on the left-hand side set, that element must lie on the right-hand side set. Okay, and because of that, because of this lemma, you don't need to use parentheses when you have multiple unions, so that B union C is going to be A union B union C. Now, it is tempting to identify the union with the addition for natural numbers. But it is not the same thing, right? When you have the union of two singletons, like say A and B, that's a pair set defined by A and B. So that if you had here, I don't know, 3, 5, and 3, you would have here the pair set of 5 and 3. But 5 plus 3, we know now, because we have introduced the natural numbers, that this is 8. And also, trying to interpret the addition of two singletons, like say 2 and 9, is meaningless, because addition is something which involves numbers, not sets. And in a similar way, trying to interpret the union of 9 and 2 is also meaningless. So you see now that thanks to this axiom, we can define triplets, quadruplets, and so on and so forth. How do you do that? Well, it's easy. You just probably abuse the axiom of union, because the triplet A, B, and C is going to be defined to be the union of the singletons A, B, and C. And the same thing for the quadruplet A, B, C, and D. Union singleton D. And so on and so forth, right? The problem is that this is extremely boring. Also, we are not able yet to define sets consisting of n objects for any given natural numbers, because we would have to iterate the operation or that operator n times. But we have not introduced, we have not defined, we have not addressed what does it mean an n-fold iteration. And also, we cannot introduce infinitely many objects, because that would require that you iterate the axiom of a pairwise union an infinite number of times. But we cannot do that yet, because we have not introduced the concept of infinity, right? But in any case, it looks quite clear to me that thanks to these axioms and to all the information that we have on our hand, some sets are larger than others, and we must formalize this concept. And we do that via the notion of a subset. And it goes like this. This is going to be a definition. We don't need any axiom, because we have enough axioms in order to define what's a subset. So we say that A is a subset of B, and we write it like this. If and only if every element of A is also an element of B, so that if you consider any object X which lies in A, that X must lie in B as well. Now, if you consider the particular case in which A and B are different, then we're talking about proper subsets, and we denote it like this. In this case, we would say that B is a proper subset of A. Thankfully, because all of the definitions, the definitions only require the notions of equality and lies in these two relations. And these two relations obey the axiom of substitution. This is something which is inherited, so that the notion of subset automatically obeys the axiom of substitution, so that A will be a subset of B, and if you have that A equals A prime, then we have that A prime must be a subset of B. By the way, for any set A, we have that A is always a subset of A. Why? Please prove it. Now, we also have that the empty set is always a subset of A. Prove it, please. Now, it is also tempting to look at this and identify it with the notion of less than or equal to for numbers. But this is dangerous. We'll carry on now with a proposition. Sets are partially ordered. If you have three sets, A, B, and C, and A is a subset of B, and B is a subset of C, then A is a subset of C. Now, also, if A is a subset of B, and B is a subset of A, then, of course, A equals B. And finally, if A is a proper subset of B, and B is a proper subset of C, then we have that A must be a proper subset of C. And again, I leave it for you to prove. But this is easy. For instance, in order to prove the first thing, this thing here, you just have to prove that every element of A is an element of C. So you pick up any element of A. And because A is a subset of B, that element must be an element of B. But B itself is a subset of C, so that X, that element, any element, the element we considered, is an element of C. And therefore, every element of A is, as a matter of fact, an element of C. Now, I'm going to finish today with subsets by introducing a useful relationship between subsets and unions. I'm going to say something also about the subset relation and the less than relation. So, first of all, if you have three sets, A, B, and C, you can show that A intersection B is a subset of A, and that A intersection B is a subset of B. Moreover, C is a subset of A, and C is a subset of B if and only if C is a subset of A intersection B. Also, you can show that A is a subset of A union B, and that B is a subset of A union B. And to finish with, you can show that A is a subset of C, and B is a subset of C if and only if the union of A and B is a subset of C. So that's the relation. There was this relationship between subsets and unions, etc. And the thing I wanted to mention before we finish today with the subset relation, the proper subset relation, and the less than relation, is the following. So this is the symbol for proper subset, and this is the symbol for less than. Now, if you consider two natural numbers, n and m, for instance, you always know that one is smaller than the other one. And that was one of the propositions of the previous lectures. So that if I give you two numbers, 328 and 13, you automatically know which one is larger, right? Now, this is not true for the sets. You don't know, and it is in general not true, that one of them is going to be a subset of the other. For instance, consider A to be the set of natural numbers multiplied by n, such that n, well, lies in natural numbers, right? I just said it. So this is a set of even natural numbers. And let's consider B to be the set of 2n plus 1, such that, of course, n is a natural number. And this is going to be the odd natural number set. So neither set is a subset of the other one. And that's the reason we say that sets are only partially ordered, but natural numbers are totally ordered. And you should also be careful about the subset relation and the Lysin relation. So let's consider these two things, the subset relation and the Lysin, or is an element of relation. Because, for instance, number 3 is an element of the set 1, 2, 3, right? But it is not true, and it does not make sense to say that 2 is a subset of 1, 2, and 3. Actually, 2 is not even a set, which is why this does not make sense. Also, while this is true, the Singleton set of 2 is a subset of 1, 2, and 3. The Singleton set of 2 does not lie in 1, 2, and 3. So this is not true. And this is because the number 2 and the Singleton set 2 are different things, they are distinct objects. And that's important. It is important to distinguish what is a set and what is an element or their elements, because they can have completely different properties. For instance, you can consider the set n of natural numbers, right? So you have this line here, and you have 0, 1, 2, 3, these are 3, 4, etc. So you can consider a set which is infinite, right? But it consists of finite elements, because 0 is finite, 1 is finite, 2 is finite, etc. But it is also possible to have a finite set consisting of infinite objects. So consider the set with the objects, the natural numbers, z, q, and r, right? It has 4 elements, it's finite, but all of them are infinite. Anyway, we will carry on next day with the axiom of separation, which is a very fun thing.